So we're very happy to have today Professor Eric Priest, who's come to us from St Andrews University in Scotland, and he's the Professor of Theoretical Solar Physics there in the Mathematics Department. He's also got a very impressive CV, and I won't even try and attempt to do justice to it. He's a Fellow of the Royal Society and a Fellow of the Royal Society of Edinburgh, and also indeed of the Norwegian Academy of Sciences and Letters. And his own expertise, as I'm sure you'll be hearing, is in the sun and in astrophysics. Professor Priest has also won a number of prestigious prizes, which I again won't attempt to read, but particularly the Hale Prize of the American Astronomical Society a few years ago is the top prize in astronomy, and was also awarded that. So, and Professor Priest has also been quite involved in the science-religion arena, in increasingly giving talks in this area, and not least, I have to say, serving on the advisory board of the Faraday Institute. So I'd like to take this opportunity especially to thank our speaker today for serving in that way. And Eric's going to talk to us today on science, religion, and creativity, a personal view. So, thanks so much.
Thank you very much, Dennis. I should apologise to any of you who have maybe come along wanting to hear a high-powered lecture on the philosophy of science and religion. I'm not an expert in this field. I simply want to share with you a few personal thoughts about what it means to be both a scientist and a Christian. As a scientist, I'm an applied mathematician up in St Andrews who works on the sun and is very interested in astronomy. As a Christian, I go to the Episcopal Church there, the Anglican Church, and sing in the choir every week and run a house group and that kind of thing. So, the sun is a fascinating object, as I hope to describe to you. It's very important for astronomy because a lot of the basic phenomena that we study on the sun are of crucial importance for what's going on in the rest of the universe. It's also important for the Earth. The sun, of course, influences the Earth in many different ways, and is very important for climate and for changes in climate. In fact, a lot of nonsense has been talked recently about the effects of the sun on the Earth's climate. So don't believe everything you read in the newspapers. I can maybe make some comments about that towards the end if you're interested. Of course, the sun is a source of light and heat and life. And as such, it's also a powerful symbol for spirituality. And each of you could write your own sermon on that, I'm sure. In fact, in the old days, it was worshipped by many different communities as a god. I was last year fortunate to visit Egypt, and there in the museum in Cairo, I saw the throne of Tutankhamun. And on the back of the throne there is a wonderful picture of the pharaoh, Tutankhamun, and his bride. And in the background you see the Aten disk, the sun god. And from the sun god there are rays. And at the ends of the rays are little hands which are giving life to the pharaoh and his bride. So the sun was very important traditionally in many different societies. What I want to do today is to introduce you to the sun, tell you a little bit about the kind of research I'm interested in, and then move on to offer a few comments about the relation between science and religion, and in particular to talk about creativity and what it means to me. And at the end, I want to describe to you probably the most awe-inspiring natural event that you can witness on Earth, a solar eclipse. But why does a mathematician study the sun, you may wonder? Well, mathematics is really a language for understanding. It gives you an in-depth way of understanding at a different level the nature of what is going on. And so it's an intriguing and very helpful way of understanding in depth the nature of various physical processes in the universe. Traditionally, there's been a very close link between mathematics and astronomy. James Gregory, I'm interested in him because I happen to hold the James Gregory Chair of Mathematics in St Andrews. He was the first professor of mathematics in St Andrews, in fact, in the 17th century. And he was, in fact, the person who invented one of the two main types of telescope that we use to this day. It's called the Gregorian telescope. He was also one of the three founders of calculus, which is the main tool that mathematicians use every day. The three founders were Newton, Leibniz, and Gregory was the third. And many of the basic techniques that mathematicians use in calculus were actually first discovered by Gregory, such as Taylor's theorem, or being able to integrate by parts, being able to construct series of various functions, and so on. These were all first discovered by Gregory. On the Sun, though, many of the surprises we have are actually caused by the magnetic field. There's a magnetic field in this room, but you're completely unaware of its presence. However, on the Sun it's different. And the reason it's different is that the Sun is not a normal gas. You're familiar with the three main states of matter, solids, liquids and gases, and you know that you go from one to the other by raising the temperature. Heat a block of ice, becomes water, heat water, and it becomes water vapour. Well, if you raise its temperature, eventually it will become an ionised gas, and an ionised gas is a plasma. It's the fourth state of matter. It behaves completely differently from a normal gas. The main way it behaves differently is that it interacts in a very subtle and intimate way with the magnetic field. The two are connected to one another and interact with one another continually. And it's this magnetic field which is creating many of the phenomena that we see in the atmosphere of the Sun. And the magnetic field exerts a force on the plasma. It also stores most of the energy that is stored in the atmosphere of the Sun. So, the Sun is a ball of plasma held together by gravity. Its radius is about 700 megameters, 700 million meters, about 100 times the radius of the Earth. And it's about 4.6 billion years old. The structure is quite interesting. There's a core, an inner core here, where the energy is being generated by thermonuclear reactions, and that energy slowly leaks out to the surface, and it's then radiated into space. That's what we see. And the outer 30% of the interior is in a very turbulent state, and it's called the convection zone. When we look at the surface of the Sun, we see the surface of that turbulent convection zone. The atmosphere itself, the two main parts of the atmosphere that we're interested in are the surface of the Sun, which is a thin layer called the photosphere, which is about 6,000 degrees in temperature. And then the corona is the outer atmosphere, which extends from the Sun right out to the Earth and beyond. So the Earth is really sitting in the atmosphere of the Sun. In the photosphere, you see sunspots, dark spots, and it was discovered about 100 years ago that these are the sites of extremely strong magnetic fields. There are tubes of magnetic field coming through the surface in these sunspots, and then spreading out and filling the whole of the atmosphere. This is a little movie of the photosphere. This is what it looks like. I don't know whether we can have these lights off here, if that's possible. You can see it fairly clearly anyway because it's such a good projector. But you can see here the turbulent nature of the surface of the Sun. Little granular cells, they're called, rise and fall at their edges, and they're continually evolving in time. This I'm going to show you is one of the best images that's ever been taken of the Sun. We're going to zoom from seeing the Sun as a whole by a factor of 100 and just look at a small portion of the disk. So the numbers on the side here, they go from 0 to 1,000, and at the end they'll go to 10. So, if you're ready, let's go. We've now zoomed by a factor of 10, another factor of 10 to go. And you're seeing the individual granules there, and at the boundaries of the granules are these little bright structures which were a complete surprise to us. We don't really understand why they're there or why they have the structure that they do. They're sites of very strong magnetic field at the edges of the little granules, turbulent granules, and it's something that's only just been discovered. We don't understand them properly at all. When we move up to the corona, this is Latin for crown, and it's called that simply because you see the corona during an eclipse of the sun, when the moon comes and covers up the sun's disk, and you see this bright crown, the corona, around the moon, or around the sun. You normally don't see it because it's about 1,000,000 times less bright than the surface of the sun in the normal light that we see with our eyes. But a big surprise in 1940 was that it was discovered that the temperature of this corona is 1,000,000 degrees, or several million degrees. You remember the surface, the photosphere, is only 6,000 degrees, and you might expect that as you move away from a hot body, things get cooler. Not so on the sun, they get hotter, and it goes up to a few million degrees. And that's still one of the big mysteries about the sun. Why is the corona so hot? We're trying to build theories and explanations of that, but it's still not yet been determined. We do know that heating is somehow caused by the magnetic field. But we don't know which of the various mechanisms that have been proposed are the right one yet. You can also see that all the structure that you see here is caused by the magnetic field. There are closed regions where the magnetic field is arching up and arching down and is containing the plasma and holding it close to the sun. And you also have these radial or open structures. These are the magnetic fields along which plasma is escaping very rapidly from the sun. It's called the solar wind. And in fact, this plasma then escapes, and by the time it reaches the Earth, it's moving supersonically, and the Earth is then sitting in this supersonic flow of solar wind. I expect students in Cambridge are just as creative as ones are in St Andrews, but they're sometimes a bit naughty, the ones in St Andrews anyway. They were, the other day, looking back on the web, browsing, and they came across a site of old posters of old movies, you see, and they thought they could improve one of these posters, and this is what they came up with. That set my imagination going, you know. I just wondered I couldn't quite remember this event in my past, but it looks quite pleasurable, really. Now, the corona, normally you need an eclipse to see it, because as I say, in the white light that we see with our eyes, the surface is so bright that the glare of the surface means you can't see the corona. However, if you observe it with a telescope up above the atmosphere that can look at the X-rays or the EUV light that's coming from the sun, then you don't need to cover up the disk, because there are no X-rays, there's no EUV coming from the disk itself. All of the EUV and the corona and the X-ray emission is coming from the corona. In fact, Helen Mason there is one of the world experts in trying to understand the nature of this extreme ultraviolet emission from the sun. You're very fortunate to have her here in this college. And this is one of the pictures, the kinds of images that we've been looking at for the past few years from a Japanese telescope called Yoko, which means sunbeam. And you can see here the corona glowing in X-ray. I can remember the excitement I felt when I first saw this kind of picture. I'd been used to seeing just the eclipse photographs, and I saw this kind of picture for the first time, and it really made my heart thump. I just thought it was wonderful. You can see the coronal holes, the magnetically open regions from which the solar wind escapes. These appear as dark structures here, and they're dark because the plasma is escaping from the sun, so there's not much plasma there, and so that's why it looks darker. You can also see the regions above the sunspots. They're called active regions, and they're brighter than normal. They're very much hotter than the rest of the corona. And we're able to, with other instruments, to look very in depth at what the structure, the close structure of these active regions is. And this is the kind of amazing image that we can get. You can see the incredibly complicated structure of the plasma structure here. So they're lining up along the magnetic field. You're seeing the structure of the magnetic field essentially here. And these are the kinds of complex structures that we're trying to understand with our theories, with our mathematics. These are in fact the equations that we use every day. I'm going to spend the next hour describing these in detail. Or maybe I'll change my mind. Maybe you already understand them, so I don't need to. But to me, these equations are really as beautiful as the sun itself. They're just fantastic. I just love these equations. The complexity of them, the subtlety of them is phenomenal. But maybe you can't understand why I think so. I need a few lectures to do that. SOHO was an enormous success. This was a satellite that was launched, and you can see the Earth here and the Moon going around it, and there is SOHO, the satellite SOHO. It isn't quite to scale, it isn't really bigger than the Moon, but it you can see is orbiting around the Sun for the first time, rather than just orbiting around the Earth. And that means it's able to look continuously at the Sun, and has given us the first comprehensive view of the Sun, and has really changed our understanding. I'm just going to show you one or two examples from this. SOHO has what's called a coronagraph on it. Here is the Sun, and there's a disk which is covering up the Sun here, and so you're able to see the outer corona. And what this instrument discovered was huge ejections here of magnetic field and plasma, called coronal mass ejections, coming out from the Sun. And when these reach the Earth, they can cause disruptions to communications, sometimes disruptions to power supplies. They can also severely damage space satellites because of the delicate electronics in them. About 40 space satellites, in fact, have been permanently put out of operation by these ejections from the Sun. On October 28, 2003, this was the picture that we got from SOHO of the photosphere, and you can see this incredibly complicated group of sunspots there. It was the most complicated that we'd seen for about 20 years, and we knew that exciting things were going to happen. And in fact, that very day, the third largest solar flare that we'd ever seen took place. And this was what happened. We saw this huge ejection going out equally in all directions. So that meant that it was either going away from us or coming towards us. And this one was coming towards us. And in fact, there was a news conference in America, and a NASA official with a military background went on television, and he said, "At this very moment, a coronal mass ejection is hurtling towards the Earth like a missile." And you can guess what happened. It was like a disaster movie. There was panic in the streets, you know, the phone lines were jammed, everyone was trying to phone up, what's going to happen to us, you know. And of course he was exaggerating. So I think he was quietly retired after that faux pas. But this was a huge ejection that was going out 5 times faster than normal. It, in fact, took 2 days to reach the Earth, but at the same time, particles, high-energy particles, were being accelerated to almost the speed of light, and these were only taking about an hour to reach the Earth and to reach this spacecraft. And in fact, these particles are creating these little white blobs in the instrument, and you can see it was almost like a blizzard. There were so many of them. And 2 days later, we saw this wonderful aurora in St Andrews. And this is looking up into the aurora. It's like looking up into a cathedral in King's College Chapel, but except that this is 200 miles high. Can you imagine looking up into this amazing structure? That's looking at it from the side. So we were all, everybody in St Andrews was out in the streets looking at this for hours. And 1 week later the fireworks continued, and by this time the group of sunspots had rotated towards the limb of the sun. It was over here, and we in fact then saw the biggest flare that's ever been recorded took place. And I've got a movie here of a similar flare showing you that's the ejections that are continually taking place, and we're going to zoom in on the site of a flare on the limb. And then the flare is taking place. Then we're going to zoom back and see the consequences of that. There's a huge eruption that goes out into interplanetary space. And so this is the power of the kind of instruments that we have now on board these telescopes. So much for my science. I'm going to come back to this towards the end when I describe the eclipse of the sun to you. But I thought now I'd move on and talk a little bit about the relation between science and religion as I see it. So what attitudes to science have you come across amongst your friends and colleagues? Maybe some of them think that science is wrong because it contradicts the Bible. Maybe others think that it's all powerful. Maybe some friends of yours in Oxford would think that. Thinking of nobody in particular. That there's no need for religion. Maybe they think that science is cold and rational and is completely irrelevant to matters of the spirit. Well, to me, all of these attitudes are misguided. I think the first one, that the Bible explains the world and so science must be wrong, is really misunderstanding both the nature of the Bible and also the nature of science. And I think in the past the Church has made mistakes by dismissing science and so has tended to lose touch with a number of genuine seekers. I think that's regrettable. We have to avoid doing that in future. Science, I think, sometimes, occasionally, deals with absolute truth. And I'm thinking especially of mathematics. A mathematical theorem, I think, is a statement of absolute truth. But I think most of science is not able to make absolute statements. It may be looking towards the absolute, but usually science, I think, is seeking a provisional understanding. It's seeking a partial understanding, one which is always being questioned, which will always be improved, which is continually evolving, maybe towards a better description, a better understanding. But this is the nature of science, it's continually evolving. For example, and in the past, many statements by scientists have been wrong, have been subsequently proved to be wrong. We used to think, for example, in the past that sunspots were planets. Some people used to think that they were mountaintops above oceans of lava. Other people used to think that they were, not so long ago, about 150 years ago, some people thought that they were holes in a solid crust above a structure that was inhabited by beings of some kind. These were the kind of ideas that were being put forward. Now we know that their nature is in terms of plasma and magnetic field. There are other statements that now seem laughable, but were made in all seriousness. Kelvin, who was one of the greatest scientists of the 19th century, said that heavier than air flying machines are quite impossible. And the chairman of IBM said, I expect a world market for 15 computers. So it makes you wonder when you read these statements, well, what statements that scientists make today will in 50 years' time prove to be nonsense? I think especially fields like cosmology actually are things are so uncertain, some aspects of cosmology, that I suspect we will have quite a different understanding in future. Maybe you'll disagree with me there, but I really think our understanding of cosmology is very provisional at the moment. So I think in future there are going to be profound discoveries about the nature of life, about the workings of the mind, the brain, about the origin of the universe. And I think that people of faith, Christians, people of other religious persuasion, should actually welcome these discoveries. They shouldn't feel defensive about them, because these are telling us more about the nature of God's handiwork. And we should welcome being able to understand better than we do now. The second attitude was that science is all-powerful, that in a modern world there is no need for God. We get everything we want from science. Well, the more I investigate the universe, the more I'm driven to wonder and to appreciate that there are many concepts that science can't explain. In fact, many of the most important concepts to me as a human being are ones about which science has very little to say. Beauty, joy, friendship, love, these are all very important to me as a human being. And they're not part of the realm, generally, part of the realm of science. The purpose of science to me is not to rival God, but it's to enhance our appreciation and our understanding of the universe. And I think our attitude to the universe should not be one of lordliness, as it was sometimes in the past, but it should be one of loving care and appreciation. To me, there are many similarities, though, between scientific knowledge and religious knowledge. I think there's some kind of underlying unity which gives us, and we're getting overlapping glimpses of the mind of God in a way. And my feeling is that Christianity shouldn't keep science at bay, but should embrace it wholeheartedly. Aquinas, way back in the 13th century, spent a lot of time trying to merge Christianity with the understanding of science of his day, the Aristotelian science. And he was very successful at doing that. And so after him there was a unified understanding. There was no such thing as a distinction between a war between science and religion, or that these were opposite senses of understanding at all. And it was really in the Renaissance that this synthesis was broken apart. And I feel that today many of the efforts of Dennis and of natural theologians is to try to bring the two back together in some kind of joint understanding. The third attitude was that science is cold and rational and logical, mechanical, that it's undertaken by computers or emotionless people in white coats. See what a scientist is. And has nothing at all to do with arts or religion. This is a common attitude, I think, among many people. But I think it's misguided. To me, scientific research in practice involves, at its core, creativity, leaps of faith, imagination, intuition, and often the scientific enterprise fills you with a sense of wonder and beauty. Often the real world is much stranger than you, and more beautiful than you could possibly imagine. And so, to me, being a scientist is a real privilege to get glimpses of this. So, if we were wanting to describe a model, a simple diagram describing the relation between science and religion, what would it be? Dennis, in fact, I hope you've all read some of the Faraday papers, these excellent summaries of various aspects, but Dennis has written a wonderful one about different models of science and religion. I actually only looked at this after I'd prepared these slides, so, but there are some similarities with what he was saying, thankfully. He's the authority in this. So, no, but if you haven't read those, I certainly would commend them to you. One possible model would be one of non-overlapping realms that Simon J. Gould put forward, that you have two completely separate spheres of activity in a way. Heisenberg, for example, distinguished between the material world, what is true or false, and between the world of values, what ought to be, what we ought to do, between good and evil, noble and base. That was his description. I think it's rather limited myself, but that was his way of looking at the distinction. I'm not happy about this because I feel it doesn't do justice to the kinds of interactions that I'm seeing between the two. Another possible model would be to think of, in a mathematical sense, of orthogonal basis states of the brain, where you have two states, one that you can describe up one axis, religious faith, and along another axis, scientific thought. The idea being that your brain state can be a superposition of these two without violating the principles of either. So this would be one kind of model, and I think this has some value to it. And I think what the creationists do essentially is to collapse these two axes onto one, and so they're losing, I think, a lot of reality. And what the atheists are doing is to ignore one axis altogether. And so again, I think this is counter to my experience, at least. I think this kind of model has some value, but I think it does ignore the kind of creative tension that, to me, exists between matters of science and matters of religion. So I'm not completely satisfied with this kind of model. Another possibility would be to describe it in terms of overlapping realms. But again, I feel a bit uneasy about this one because I'm not quite sure what goes into that region of overlap. And in a sense, it depends what you mean by the circles. Do you mean the techniques or the way of looking at things, or do you mean the subjects you're studying? It depends a little bit what those circles are referring to. I think there's a fourth idea which to me makes more sense, and that's to talk in terms of a kind of fuzzy boundary between the two, some kind of interaction region where you're tackling the same reality but looking at it in different ways. in Dennis's paper I read after I'd done this that he actually describes this as a complementary model, I think, essentially. This is maybe a diagrammatic way of expressing this. And but to me it's important that both of these ways of looking at the world are immersed in a commonality of what it is to be human. That essentially creativity, beauty, wonder, the social aspects too, these are all part of what it is to be human, and these all have an effect on both the science and the religion. So that's just an idea. See what you think about that. But what about the points that sit on this interaction region? Because that's the interesting region where you've got the tension between the two, where both are contributing to a deeper understanding. Well, things like the values of universal constants that a lot has been spoken about, the form of the physical laws, the origin of the universe. These are huge questions. The appearance of life and complexity, the nature of consciousness. The fall, I think, is an interesting one. How do we bring a scientific, what would the scientists say about original sin or morality? I mean, there's a lot of interesting research being done at the moment on whether higher animals actually have a sense of morality or not. There's some suggestions that maybe they do, which is quite interesting. The relation between different ways of knowing is something that Aquinas wrestled with a lot, and I think this is also interesting. What is the value of the different ways of knowing, and how are they related with one another? Providence too is something that interests me. How does God sustain the world? How does he act in the world? What's the nature of miracles, and so on? I think these are interesting questions which theologians can debate, but which I think scientists can maybe have an impact on. So, to me, you can be both a scientist and a Christian, but only provided science recognises these natural points of contact, and only if religion turns away from a too literal interpretation of the scriptures. That it recognises when these scriptures were written, by whom, for whom, and for what purpose. And that's distinct from how you use the scriptures today, and what they are of value to you today. For example, the Bible speaks of the origin of the universe, the makeup of the universe, but I think it's not doing that as a scientific account. It's doing it to describe the relationship as the writer sees of humanity and creation with God. And that's quite a different purpose from a scientific purpose. You can be a scientist and a Christian, I think, but only if science recognises that there are questions which the scientific method cannot answer. There are many important questions which science is incredibly important in our lives, but there are many questions which science cannot address. And also I think it's important that religion doesn't challenge scientific facts with ideas alone. Religion should welcome the role that science has and what it can offer. This is an interesting little quote which I think suggests that science and religion actually can, when there's a healthy relationship between the two, they can both help one another become richer. So the quote says, "Science can purify religion from error and superstition, and religion can purify science from idolatry and false absolutes." And I added on the end arrogance, I think, as well. I wonder if you know who this quote is attributed to. Anybody come across it? It's actually Pope John Paul II. Interestingly. Now I want to just move on briefly to say something about creativity and what it means to me. I think the creative moment can come at any time, but the important thing is how to cultivate creativity, how to keep it alive. One way is to question everything, the principles, the basis, the hidden assumptions behind what you're doing. The second is very important, and that's to create space, to create the environment within which creative moments can arise. And I think this is one of the real problems in modern life, that we're often stifled by the modern pressures. And I think those of you who are scientists will recognize this. I think it's a real problem at the moment. So don't work too hard. Give yourself time to play, to think, and therefore to make these new connections. I think this is so important. And try and develop these creative skills that you have to think in the right ways, or to see things in a new light. Keeping informed and up to date is also crucial. I think one needs to know one's subject well, to understand the problem in depth, to read broadly. These are very important. Pasteur said chance favours the prepared mind. In other words, you have to do the work beforehand if you're going to have creativity that's going to be effective. And work hard, you know, at the techniques and so on. Perspiration, I think, always follows the inspiration. Both of them are essential. But if you just have the hard work without the inspiration, then you won't be doing anything worthwhile. So they're both important. And being motivated, I think being challenged by a problem or a puzzling observation, really feeling challenged and following your passions is important. Loving your subject essentially, and having tenacity, keep nagging away at it, don't give up, you know, this is really important. I had an interesting meeting with a poet, and this was part of a project that our professor of English was conducting. He asked me if I'd like to interact with a poet, and I thought that sounds fun. Yes, why not? So I had lunch with him. His name was John Glenday, and we compared what it was like to do science and to write poetry. And this was a real privilege to me. I told him how I really had an urge to understand the complexity and the subtlety of the sun, and to communicate with people what it was I'd learnt. And John also himself had a keen awareness and care for people and for problems, and wanted to communicate what he understood in new and pithy ways. This was the object of his poetry. For me, the ideas are continually floating around in my mind, but suddenly one of them will take on a life of its own and will crystallise. And then I'll know the general direction in which I'm trying to go, often, but I won't know the way to get there. And then I have to use all my skill, all my mathematical techniques to try and get to the goal. And John said, yeah, that's what I do when I wrote poetry. So it's just exactly the same. And then he was commissioned to go away and write a poem about our discussions. I just had to go home and enjoy myself, you see, or get on with my latest piece of research, but he had to then work. And he said normally it'll take me maybe 2 months to write 6 or 7 lines of a poem, which amazed me. I thought that if you're a poet, you sat down and it flowed and that was it. But no, he said you really have to work hard at crafting each individual word and working at what to do. So I had no idea that that's what poetry was like. Anyway, 2 months later it arrived, by email of course, and he said he had an interesting time producing it. It was almost willfully unscientific though, he thought, but he said that what impressed him was that so much wasn't the work that I was doing, but the belief behind the work. So that's what he noticed, and his main interest was to what extent the science or the art reflects our humanity. and he felt that he'd seen that in the work that I described, so that was quite humbling. And this was the poem. Rise over me in the morning, lay yourself under me as the darkness breaks, then ferry me like death, like sleep, like memory, back through the hidden workings of the night to a place where everything lies buried and begins. That was rather lovely. And then he was just commissioned to write one poem, but he then went away and said, when you talked about the circular shape of the sun, that reminded me of the Buddhist notion of a circle, of the soul as a circle without circumference, and also reminded me of Da Vinci's drawing of this idea of Vitruvius, that the human form embodies perfect forms, the circle that you can see here, and also the square. And he had these ideas in his head when he started on another poem. And he said, I feel as if I'm working with absolutely nothing as the raw material, and somehow managed to create something. The final lines try to describe our relationship with the soul and the creative act, he said. And this was his poem, Vitruvian. Then there was a time I tried picturing the circumference of the soul. But the best I could manage was a shimmery milk blue sun, like an oversized thought bubble or a zero with my height. Which immediately reminded me of that hoot he once transcribed through a sweep of his sepia arms. As he reached out beyond the trammel of himself and caught hold of nothing with both hands. It's rather fun. Just very quickly, I know I'm running a little behind here, I just want to describe this eclipse of the sun that we saw in Egypt. This is the shadow, a little movie of the shadow of the sun going across, and the central dot is where where you get a total solar eclipse, where the sun is completely covered up by the moon, and it just forms a very thin path across the surface of the earth. And this was crossing the Mediterranean just here on the border between Egypt and Libya, and that's where we went. That's a picture of the shadow cast on the earth, and that was just proving that we were in Egypt with a rather pompous friend there. And we went to Alexandria, to the new library that was opened in 2002, and I had to give a lecture on science and culture to 850 young people. That was a little, after the lecture, they kind of came to me in little groups of boys or girls, and this little group came and asked me lots of questions about science. And at the end of all these questions, I looked around them and I said, you're mainly Muslims, and I'm a Christian. I said, my feeling is that we worship the same God, but we worship him in different ways. I feel that we're sister religions, and that we must do all we can to improve relationships and understanding between our two religions. And Hadia here had tears in her eyes. She said, I never thought I would hear anybody say something like that. All we hear on the television is that the West hates us. We just hear about Abu Ghraib and Palestinians being slaughtered and Iraq and the Danish cartoons. We just thought the West hates us, and you're coming and telling us something completely different. So I found that quite a moving moment, and I felt that it is important for us all to do our own little bit to try to improve the understanding. Anyway, let's go on. This was the site of the eclipse. It was on top of this plateau in the desert, and they'd set up two 20,000 tents for us to sleep in. That was the start of the eclipse, and the moon is moving across from right to left. And over the 1.5 hours that it took the moon to move across, the light level gradually decreased, and it got cooler, and the shadow sharpened. That's a picture of my shadow. Quite unlike a shadow that you would see now, which would be quite fuzzy around its edges. It's just uncanny. And this was the Bedouin tent where we were having our food, and it was made out of a kind of fibrous material. And somebody said, "Oh, look," and they looked at this tablecloth, and there you could see lots of little crescent suns because of the light coming through each of these little holes in the fibrous material. And in the last 10 minutes, it was quite remarkable. It was just like somebody turning down the switch on the wall. The light, you could feel the light getting cooler and cooler, the temperature getting cooler, both of them decreasing, and there was a wind, because the air was rushing into the place that was cooling. And you could see the planets in a line. Because of course you're looking at the edge of the disk in which all the planets are circling around the sun. And in the final minute you saw things called Bailey beads and the red chromosphere. And then the corona glowing white against this jet black disk. It's quite remarkable. That's just before the moon uncovers the sun. Covers up the sun. These are the thing called Bailey beads, and this is, you can see the red chromosphere there, which is the layer between the photosphere and the corona. And that was what we saw. Quite amazing, so beautiful. And we just gazed at it in wonder. All these structures being created by the magnetic field. That's another picture that someone took. Quite remarkable. And looking around on the horizon, you could see a kind of sunset around it through 360 degrees. You can see all the people there as well, all looking upwards. This little group in the corner, take a close-up. There's always one, you see, that's looking at his mobile. Missing out on what's important. And then just as the moon begins to uncover the sun, you start to see the chromosphere again, the red, and the Bailey beads. And then this is called the diamond ring effect. This is the diamond and the ring of white around the moon. And then it's over. You have to look away. And you wish you could turn back the clock and experience it again. But you know that the only way to do that is to travel maybe in a few years' time to some distant part of the earth to be able to see it. Quite remarkable. So my conclusions, anyway, that the science of the sun is fascinating. Part of being alive and human is nurturing this creativity, listening to the still small voice, if you like, making space for these ideas to grow. Sometimes I think science is absolute, but most of it is provisional. And I think the Christian life is very similar. It's a voyage, it's a pilgrimage, just as the scientific life is. In science, we have to question everything. But there are many questions that you can't answer, and that all you can do is wait patiently. And when you're grappling with these answers, it's very important to have integrity, to be true to yourself. I feel that most people will not believe the claims of Christianity by being forced to do so as children or as adults. They won't do so if the existence of God is proved mathematically. But they'll only do so when it resonates with their experience, I think. The way of the scientist, in my view, is open, sensitive, listening. It gives you a profound sense of beauty, of wonder, and of mystery, and also of humility, because you realise how little you understand. For me, it is possible to be a Christian in the scientific world if you're open to the insights of science and if you're responsive to the hand of the Maker in the universe. Now we see through a glass darkly, but then face to face. Thank you.
Thank you very much, Eric, for this fascinating overview. We did start a little late, so I'm sure we've got a few minutes for questions, and then we have to finish. Yes, the question over here.
Dissenters from the idea that the global warming we're seeing, which we're told is going to increase dramatically, is all due to man's activity, have suggested that it's really due to the cyclical variation in the sun's activity. What's the truth?
That's a very important question, and there's been a lot of misinformation lately. When you look back in time, you find that there's a clear correlation between the activity of the sun and the climate of the Earth. The activity of the sun goes up and down, it varies over long times, and there's been a clear link in the past. For example, in the 17th century, for a period of about 70 years, there were no sunspots at all. The sun was very inactive, and that was a time of very low temperatures in northern Europe especially. It was called the Little Ice Age. The River Thames froze over, you could drive a horse and cart across the Thames. So there is a very clear correlation between the sun and between climate. Now, an important point is, though, that we don't yet understand the mechanism. We don't understand how it is that the sun is influencing the climate. There was one view put forward, which is probably the minority view, on a Channel 4 programme about a month ago, and it suggested that it was due to cosmic rays, that cosmic rays were the ionisation trails from cosmic rays coming in were acting as seeds for water vapour, and that now that's true, it could possibly be happening, but whether that's enough, whether that's dominating all the other seeds for water vapour is a huge scientific question which has not been answered. And then you see what happens is that when the sun is active, the magnetic field in the interplanetary medium is stronger, and so the cosmic rays are diverted around the Earth, so you get fewer cosmic rays hitting the Earth. So that's one idea. I think it's unlikely myself. Almost all climate scientists that I speak to don't believe that that's what's happening. The other possibility, which has been investigated, is that although the light that we see from the sun, the white light, goes up and down, it only varies very slightly by maybe 0.1%. And that's not enough to create the changes that we see in climate. However, the ultraviolet light from the sun varies very much more. And the ultraviolet light, the extreme ultraviolet light, is absorbed in the upper atmosphere, in the ozone layer. And so it's possible that somehow that is affecting the lower climate of the Earth. But whether that is the case and just what the mechanism is, we don't know. So there has been a clear link. We don't know the mechanism at the moment. However, the key point is that now that link has been broken. For the last 30 years, there is no longer a clear link between what's going on the sun and between the Earth's climate. So I don't believe that the current global warming is created by the sun. In fact, if you look at the carbon dioxide content of the atmosphere, it goes up and down. Every time there's an ice age, it goes down, and between the ice ages it comes up, and we can go back for about 1 million years, and it always comes back up to the same level, 270 parts per million carbon dioxide in the atmosphere. At this moment, the carbon dioxide content is 380 parts per million. So the amount of carbon dioxide that's present in the atmosphere of the Earth at the moment is very much greater than it has been historically. And it's that and the other greenhouse gases which are undoubtedly causing the increase in temperature that we're observing. It's not the sun.
Thanks very much.
Sorry for the long answer, but I think it's important to get that clear.
We've got time for one more quick question, then we're going to stop. So if anyone has another question, otherwise I think perhaps I know Eric's taxi doesn't leave until 2:30, and so if other people have questions, do hang around, and I'm sure you'll be happy to answer other questions personally. But I know some people have to go. So again, can we thank Eric Priest very much indeed for a fascinating talk.